I think I want to back all the way up to what we think of in history as the first moment of science. Right? At this point in history, there was some very, very, very early philosophy happening. And then the first scientist, the one I'm going to call the first scientist, will be Alexander, who became the first scientist by being the first person to go about his activities, to engage with the world, and come to a reason to need to systematically make measurements, to systematically compare things of different lengths in time, things of different lengths and distance. Okay, so this was a huge, huge revolution. This was a connection that hadn't been made before, and it transcended him to a world much, much more familiar to the world we're now in. Right? There's a very specific thing that happens when you become a kind of conscious creature that uses measurement to correct your conscious framing. Instead of just engaging with your conscious framing, bad guy, kill, run, whatever decision you have and just committing to it completely. Instead of just doing that, you're making a framework, making a story of what your environment is, of what the reality is, but then you're testing it. You're literally examining the details of the story for things that you can go check against in the real world. Now, the only way to check is to, how did they do it up until then? I mean, it was a much more loose concept check before that. You would go ask your parents, you would go ask your friends, you would go ask whoever you thought was a respected person in that domain of thought, and you would take their word as validation. That's as far as it could go. And they too could only be guessing, right? They weren't at any point measuring anything to validate the story they had about the world. Here comes along Alexander, and one guy, we believe, completely transcends what it means to be a conscious being at that point. He goes from someone who's trapped under that horizon to realizing I can engage with the real world specifically, systematically, and do something more with it. Right? What did he do? He invented maps. It's incredibly, incredibly relevant to the modern way of thinking. Right? Maps are commonplace now. We literally map our routes almost every place we go, right? We're familiar with looking and thinking in ways of maps. Alexander invented maps. He invented the notion of taking a picture of something, look out on the horizon, and you see some sort of landscape, right? And you want to talk about the landscape. He decided he wanted to talk specifically and exactly about the landscape, not about your opinion of it. What a big change, a completely different way of thinking. He wanted to validate things not by using anyone's opinion or anyone's authority on the topic. He wanted to use only things that could be way more accurate, measurements from the real world. But what can you measure? He invented measuring. Here we're measuring and we're mapping relevant distances between things. You can map points to points. You can perspectively connect things. So making an actual image of something you see, logically exactly all the things in it are being mapped one-to-one into some other frame. You now, first of all, have to pay attention to way more details, but you're systematically now getting distance measurements against distance measurements. You're getting a basic arrangement for the whole framing of geometry. Okay. Also, he invented one other thing, measuring time. He measured time by putting a stick in the ground. The sun shines and it has a shadow. But the sun moves during the day, and so the shadow moves too and has a path. And you can go along every couple minutes and mark this. If you haven't done it, try it. It's a great thing to do. Mark the path. You can do this over the seasons, and you'll see that day by day the path comes in and out also. You can get a lot of information from this, but most importantly, it's the first way humans had measured time. Not guessed about time or roughly talked about time in a sentence, measured it. Like went into the world and actually took a measurement and associated a number that you could then later compare to a different number that would reveal relationships between them. It's a different way of looking into the world because measurement always gives you excess powers, right? It gives you the ability to look further. Literally, you're looking at more detail, more accurately with measurement than your senses just do automatically on their own. Your senses, first of all, let's just give that they're perfectly accurate. There's no mistranslation of information as it's coming into your brain. Still, if that were the case, your brain is still completely responsible for making up the story of what it meant. It has to turn it into a story. So since your senses are all the time taking in data, your brain's translating the data through the framework of what it thinks reality is. So it thought that meant what it sees, right? The way you see is what you believe about the world, literally. And as we have evolved through history, not genetically, as we've evolved through history with different concepts, right? Those different concepts have taken us to places where we could see new things. Things we didn't ever notice before, okay, but are there. Built-in features of reality, there's absolute surprises at first, but they tell you something about reality, something you weren't seeing before. All right, so the first scientist comes along and single-handedly invents measuring time and space. Invents maps, of course, because making systematic measurements of space basically is a map, right? And the first form of a clock. I would try to imagine the impact of removing all clocks and all maps from the world. What's left? There's still things left. You didn't get rid of everything, right? I mean, in the past, we didn't have clocks, we didn't have maps, and humans still existed. But the world we conceive through right now, the entire media stream and network that we use, all of that goes away. All right, so I'm really trying to impress the importance of this small idea. You'd think it's an easy idea, right? I mean, it's not that hard to get. Why? Because in our world, it's obvious how relevant it is. But try to transport yourself back to Alexander's world, where there weren't any other clocks to compare his clock to. There weren't any other maps to talk about in comparison. There weren't any other people doing things, engaged with anything to do with that. The concepts that we discover by learning how to look further into the world, not concepts we discover by making them up, or it's concepts we discover by looking further into the world, by discovering how to look further into the world. Every time we do, every time someone in the group of humanity does, as long as their ideas don't get lost, it takes us to a new set of what's relevant parameters. A new world where the different things matter to you. Think of what sets what matters to you in this world. The thing that's most important, money. Because the money is the backbone of how you get all of your everythings. Right? If you want to get any ingredients, you want to get food, you want to get supplies to fix your house, you want to buy a shovel to dig a hole. Anything, well, people are all resource consumers now, but through the network of money, through the way we distribute resources. That's what's relevant to us, right? It's extremely relevant. That's how you eat. That's how you survive. But in the past, there was no money. It wasn't relevant at all. In the future, I'm imagining, or the future path I want to connect between the story of when science starts from Alexander to where science is trying to take us. I'm trying to make it really clear. Science is the thing that's offering consciousness its evolution. There are other things, of course, that offer evolution to your consciousness. In fact, every new experience, every new engagement with actual reality that you have trains your brain a new way about new degrees of freedom in the world, about new things you're now noticing and engaging with. So your consciousness actually evolves the greater your complexity of involvement is, right? But in the other sense, your consciousness evolves as the story changes. So some things that evolve your consciousness make you more aware of new features. You go somewhere, a new country, and there's a whole set of new kinds of food. But it's still food. It's not changing the laws of physics. It doesn't really radically make you change the rules of the world. Okay, there are discoveries that once you discover them, you can't go back to the old world. You couldn't ever want to, because you discovered a world that makes far much more sense of far much more things. And it invites you to pay attention to details you weren't paying attention to before. Details that give you new control over your world. Not complete control, that's the goal. Complete control would require complete understanding. You need to understand all the degrees of freedom building up your environment and your world, everything relevant and involved, in order to have complete control over it. But as that goes from completely vague, right, looking into the world and getting the story entirely wrong, to getting details right, more and more right, using things like measurement to hone us into actual accurate perception of reality instead of just stories that we go by from our first guess, from whatever our brain made up, our sight, literally just our brain's guess. All right. Along the way, the discoveries that end up really impacting the world are discoveries like discovery of electromagnetism, electricity, magnetism. These are features in the world that were completely buried in the umbrella, under the umbrella of magic before, right? They showed up in lightning, they showed up in St. Elmo's fire, they showed up in magical events that happened in dramatic times of people's lives, really easy to cast into stories and make them feel like they're ghostly things. Okay, so we didn't have a very clear understanding of any of these features, let alone that they were related, right, starting out. So the discovery of each new feature of the world, whenever you discover something that's actually there that no one knew before, like the electron, it changes the world we live in, obviously. It changes the world we now have electricity. It's such a dramatic change to be able to use the earth we were already on in a new way to make electricity. Right? That's such a dramatic change. I mean, that's kind of an obvious statement these days because it became entirely relevant in the network of most of our attention spent on. That wasn't so obvious before. My point is that we are not done in that story, right? We don't have a theory of everything. We haven't finished the goal of science. And the goal of science is to wake us, the person who's doing the science, to wake their consciousness up to another higher level of consciousness, to keep going through that progression that you start when you're a baby and you don't know how to walk yet, right? You're literally trapped to just what's right around, but you don't think of it as being trapped to what's right around. Everything outside of that room doesn't exist. It takes a long time for your brain to map other things and extend past where you've been and try to guess to the world, right? It's just the parts you've explored that are there. We have further to go, and we know exact stages and steps of things to take advantage of still that aren't being taken advantage of. Just like the discovery of the electron led to this whole revolution, the discovery of the other features still remaining, right? All the ones that are buried in the mathematics and no one has actually an understanding of why that feature's there, what it's really telling us. Those features have properties available to us that we're not using. Properties like electricity. Okay? And one of the main features we know for sure it's holding is a transference between matter and energy. For sure, that connection has to be built into the rules, right? So whatever's going on in nature to keep all the rules of quantum mechanics and general relativity balanced, there's a transference in those rules between matter and energy. Energy can go from being pure energy in the form of light, going the speed of light through the medium, to being completely wrapped up, having an actual position over time. This is the famous E equals mc squared. Energy of something is equal to its rest mass times the speed of light squared. But its definition of how much energy it has depends on how much mass it has, and then times that mass by the speed of light squared. Take that mass and make it go the speed of light 2 ways, whatever that means. That's what the math is trying to tell you, right? We're marrying mass with the speed of light 2 ways. And that is energy. Those two things are the same. So if those are equivalent, you should be able to slide between, go from one to the other. And that's that's what we believe today anyway. But the point is, even though we've made the atomic bomb, even though we've extracted the enormous, see how much bigger we got mass in kilograms, this is meters per second, but this numbers times 10 to the 8, and then it's squared. So when you multiply mass by this number that's squared, it becomes much bigger. The energy becomes huge, right? So that transference is a huge deal. When you do that, you get an atomic bomb, say. Take mass and you convert it to energy, you get an atomic bomb. So we know we can get that energy out of mass. We know it's there, but we don't know how without putting things to ridiculous high levels and smashing things together, high temperature, high pressure, to just force it to happen. We know it can happen naturally, okay, without it being forced to happen. So the point is, at this stage in history, we're completely aware as physicists, as conscious beings exploring our world and trying to get a sharper and sharper, more detailed picture of what that world is, to the point where we can explain all of its inherent impregnated constants and features and symmetries and so on, right? When we can do that, we should be able to take energy from mass. Think what this changes. Think literally, this changes if you have access to mass. And I'm standing on some right now, so I'm good. If you have access to mass, and you have a conscious framing of the world that's correct, if you had the theory of everything, if you understood how things actually fit together in a coherent way, and it worked, it gave you insight and predictive power of everything that's going on, right? If this was built into your understanding of the world, not just a memorized equation, this would empower you to use mass as your energy source. All right, so if you have local access to mass, if you know how to convert it to energy, or along the way to any other transform, energy is complete conversion to light. If you have one matter arrangement and you convert to a different matter arrangement, you can convert to that too. If you know how to if you understand the internal structure, you should be able to convert matter, once you have access to it, to any other arrangement that is up to, equal to, the amount of mass you started with. There's a lot more to take advantage of in the world. A lot more to take advantage of. When we get where we're going, we won't have, I shouldn't even say it like that. When we get where we're going, it's not that we won't have to use money, it's that it wouldn't even occur. It won't be relevant. Think of this. Money won't be relevant. Okay? Why? Because when you know how to convert energy, when you know how to convert matter to energy or to any other arrangement of matter of less mass, you no longer need to go anywhere to get your things. You see what I mean? You should be able to use all the periodic table of elements, all of those elements, to restructure, reorder things, flip things around, move electrons around on purpose. You should be able to use on purpose, like a computer program, to do chemistry on the actual physical transforms that are going on in physics. Put short, you should be able to do the chemistry that nature does now. Growing plants and trees and all the things that it can do, making gold and silver and all the things it can make. You should be able to do that on purpose. That's a level of living in the world that's completely different than the one we're in right now. We're all slaves to the system of resources. In the future, we won't even know what that means anymore. Everyone that feels doesn't have enough resources, here you go. I replicated you, a replicator. Anything you can imagine. You just have to busy yourself now with getting good at imagining. That's the future that we're really pushing for. And that's how I see what science is aiming for. The system we have right now is not empowering. That's my opinion. And I think this will be. I think this will take us to a place where what matters is your personal development. What matters is your consciousness getting to have its chance today to step up a little, to see further and be aware of things it wasn't aware of before, to be making connections between things it was aware of before much more fluidly and exactly. The goal is to be able to see. Think of this. Science's ultimate goal is to create an individual that opens its eyes and sees the real world. That's really what we're after, because we start out blind. We make up a guess. We practice seeing that made up guess, and most of us get stuck there the whole time. Actually, back up. Other people practice for us a made up guess. We see that, we practice it. We get stuck there because we're not in the practice of remembering that we're guessing. But every now and then, finally, someone comes along like Axanamanter and says, all right, but I want to know better than my guess. He was honest enough and cared enough about looking into the world that he wanted to measure. I mean, think of this. If you measure, what's the chances you were wrong? Most of the time. So he was expecting to be wrong, and he was willing to be wrong. That's the thing that it takes in order to measure, right? You have to be willing to be wrong about your current story. Let's go to the next stage and talk about the actual details of that process, trying to look further into the world and discover the symmetries, the built-in hidden patterns, the logical relationships built in. Okay, now this boils down to a conversation about, I'll start here, the constants of nature. Now let's pause here so it's very clear why I'm bringing this up. The constants of nature are to be thought of as the clues we've found about the world from using this new superpower of measurement. Okay? And here's a really good thing that comes with these. Constants in nature, measurements, they also come with error bars. So you have a confidence interval in the number itself. You know at what level do I know this for sure and what level do I no longer know it. Okay? This is a powerful feature. We didn't have that before. When you look in the world, you're not checking any. I mean, you might check the stuff you get up to and roughly touch or run into and find out you were wrong. But if it's in the distance, okay. So the constants of nature give us a whole list of discovered features, symmetries, rules built in, geometric constants, common list, the speed of light, Planck's constant, the gravitational constant, the electric constant, the magnetic constant, and so on. There's a whole long list. And really, this list is a list of different dimensional relationships. Like, there's not a uniformity in the dimensional expression that this list has. They're not all one-dimensional things. Okay, in fact, they have many different kinds of dimensional arrangements that the numbers of each of these constants refer to. Okay, But some of the constants, like if you take the mass of the proton and the mass of the electron and divide them, well, the mass divided by mass goes away. And you just get two numbers that give you a ratio. That seems to be a built-in feature that's dimensionless. What does that mean, have a dimensionless built-in feature? The most popular and central dimensionless feature in all of the constants of nature is pi. That's interesting. If you know about this number, if you've discovered its existence in the world, what it means about the world, you're going to love that one being in there. And there's another one that we call the fine structure constant. It's dimensionless, just like pi, right? Pi doesn't have, pi is, well, I'm going to say, okay, equals 3.14159, and then we say dot, 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 right? So it's approximately the first few digits of this. It doesn't ever end in meters. The units of pi are in meters. No, the units, it doesn't have units. It's dimensionless. It doesn't have units of seconds, coulombs, anything. It's dimensionless. Just like the fine structure constant, it's dimensionless. So this is a geometric number built into reality that has not been explained. It says something geometric on the level of how pi says something geometric, and it's related to pi. That's interesting. They're both there in the constants of nature, mainstream stars on all the left-hand sides of all those equations. Okay? They're really built in. So if you have the measurements of the constants of nature, and you play around with comparing them, and you want to get systematic about trying to tell the story about what these things are saying, and find the symmetries built in, find the relationships built in, and find the geometric story of those relationships, right? If you start doing that, the thing you run into first is that there are limits built in. Limits built in. What do you mean limits? Limits to the 5 dimensions. Now, I really need to take a break here, or a pause here. There's limits to the 5 dimensions, but more than that, every one of these, let's see, we got 288 constants in this list. Okay, every one of these constants has associated dimensions to it, and all of those dimensions break down to being composable from just 5 things. Just 5 things. 5 different dimensional ingredients. One of them is time. This is a huge discovery, by the way. Remember, we're talking about the things we can measure, and time was the first one discovered of the thing you can measure. The next one is space, or length, okay? And the next one is charge. This is less familiar conceptually, which is a big cue that you're not seeing the real world yet, right? That's exciting to me when I know for sure. I know a clue that tells me I'm definitely not seeing the world right, because that's a real built-in feature and I don't see that feature. Time, you know how to measure. You know what that means to say making measurements of time and of space. Charge, if you don't have any picture for what charge is, you're completely lost about a measurement of a charge is, right? Mass, that's familiar. And temperature. Okay, so these 5 dimensions, this is one of the big discoveries here when you play around with all of these data points about the secret code of reality, if you can think it that way, right? These are the actual clues that are still undecoded about what reality is. There's no question about whether the speed of light has a role in the structure of reality. There's no doubt about that. The question is, why is the speed of light what it is, right? And so on, all the way down the list. All of them are composed only of components made from this small list of 5 things. Okay, like the speed of light is made out of Speed is length divided by time. So it's the Planck length divided by the Planck time. Or dimension-wise, it's going to be just space divided by time for its dimensions. Okay, so more than this, when we compare, I think I started to give it away here, when we compare these constants, remember these aren't things people see in the world yet. These are features still available to our conscious evolution. When we compare all of them, we quickly discover that we can play a fun game. If you have one that has units of like time and charge squared, if that's the units of the dimension, has a string of numbers and power, and this is the dimension. You might find something else that has charge as a dimension. So you multiply this other one that has charge, so this would be constant 1, which has dimensions of that. Okay, multiply it by some other constant, I'm being vague right now on purpose, some other constant whose dimensions I want to specify, and I want to cancel charge, right? So if I multiply, it only has charge, say, as its dimension. So I square it. I square the number, square the dimensions, okay? And it cancels charge squared. Now this number squared times that number squared is a representation of time, right? Okay, when we play this game with the constants of nature, comparing every constant of nature to every other constant of nature, getting all the ones that are close in dimensions so that they can cancel out relevant things and so on. When you play that game, you discover quickly that there's numbers that pop out over and over. When you try to reduce to a single dimension, you end up getting very special numbers. These are the cutoff boundaries in the balance of physics, in the actions of physics. These actions themselves, when they are happening, which means matter is around, and when matter is there, when things divide like matter does, or when matter is present, then these boundaries are present. Okay? Very interesting. These actions imply special boundaries. And these boundaries are the Planck time, there's the symbol for it, the Planck length, the Planck charge, QP, Planck mass, and the Planck temperature. There are geometric truths waiting to be discovered in the actions of physics. Let's start with what I think might be the most famous one. E to the pi I, how do I want to write it? Plus 1 equals 0. I think this is got a good argument for the good way to write it. This is a very famous equation, and why?
It's got 5 of the most important representations in all math, isn't it?
Yeah, 0, 1, pi, I, e, plus, and equals. If you include those, that's a real good set, right? Somehow there's a built-in relationship. That's the thing that's really surprising. This equation reveals that there's a relationship between those numbers. We are very interested in the relationship between numbers. These special numbers. Algebraic geometry is the story of the relationships between numbers. When your brain becomes aware of that extra degree of freedom, that new feature of the world, you're now going to be mapping a greater world, right? You're going to be somebody who can do things you can't do now. Completely. Think when you have a replicator, right? When you can transfer energy or matter to energy. That's something orders of magnitude beyond what we're doing right now. Okay? And when you can do it with control, that gives you access to things we're not even conceiving right now, like personal space travel. Okay? No longer is it a logical issue. It's doable at that point. So this is, you can rewrite this, of course. E to the pi I equals minus 1 to make it shorter. So this is also a way that's very a favorite because it's very short. And it makes it really stand out. Like, what does pi and e have to do with -1, right? It seems like a mystery when you first find this secret built into algebraic geometry, right? It's a secret built into the world. Let's do another one. I to the -I squared. I to the negative I squared. Lots of ways you could rewrite that. I could pull the 2 down here, I to the negative 2I. I could put that in the denominator. But let's just go with this for now. I to the negative I squared. That equals e to the pi. And you might remember from earlier lectures that e to the pi is also equal to the infinite sum that gives you the total volume of even dimensional hyperspheres, right? That sum equals e to the pi. So this is the volume sum of even dimensional hyperspheres. That's a geometric number. What is it doing with I?
Good question.
All right, there's a Q here. So the big thing about the treasures of algebraic geometry is when they're first discovered, they're shiny treasures. They're, wow, I can't believe this. This is a connection I didn't see in the world. But that connection has a secret, right? That connection wasn't seen for a reason. You weren't seeing what it connected to before. And now looking at it can lead to more discoveries. So finding these prescriptions in algebraic geometry, these rules between something that can be defined as something geometric, maybe you don't fully understand that geometric thing, but you get clearer and clearer picture the longer you investigate its features. Okay, so where I want to go next, in our last video we talked about the equation for the hyperbolic figure 8 knot, the diagonal structure, right? Okay, at this stage I want to show something really beautiful in our algebraic geometry. We have 3 units that we really care about in this picture, where we draw xy plane and we put at 1 here, we draw in the unit circle. Okay, this unit circle has a radius that we care about, and our story right here has a 1 length and along the axis, and it has one that goes up to here with a length of 1. Its radius is 1 still, but it's in this other direction, so we call it I. All right, and then we have in our picture one that's roughly here that we call the imaginary golden ratio. All right, 1 squared, cubed, fourth, fifth. Every time, doesn't matter how many times you take it to power, you just wind back to there. You land right there. Okay, with I, if I take I squared, I land right here. Right? I do another rotation of 90 degrees, the same rotation it represents. So every power of I provides another copy of the rotation of I. So I squared here, I cubed here, I to the 4th here. Now you can keep counting up I to the 5th, but it kind of becomes redundant because I to the 4th became the same thing as I to the 0, right? It becomes 1. Let's write that down. So I squared equals -1, brought us over here. I to the 4th equals 1, brought us all the way back. So there's 1 I, there's 2, 3, 4, right? So in rotations, we do them by powers. 1 goes all the way every time. 1 squared, 1 cubed, okay? But these guys, they're divisions of that whole circle. They're less than that 1 circle. So in comparison to the 1 circle, I divides 4 ways, right? It has to go all the way up to the power of 4 before it gets back to 1. The imaginary golden ratio, let's also say I equals -1 to the 1/2. Kind of obvious here, but I'm going to compare that now to the imaginary golden ratio. So the imaginary golden ratio cubed equals -1. And the imaginary golden ratio to the 6th, 1, 2, 3, 4, then 5, and then 6. So 6 times around till it gets there equals 1. So there's a symmetry, of course, between these two, right? One's 2/3 of the other. And I can write down the imaginary golden ratio as -1. It's a flip to the 1/3. It's a third of a flip. Now, so far we did all this last time, except I didn't really focus on this one, this thing that you go in powers and just ends up back at the same place. But it's a feature that's built into it. I mean, these both have a radius of 1, first of all, but there's going to be a 1 that matters that these are comparing to. So what I want to do is now look at our dilogarithmic structure, the one that gives us the features of the hyperbolic figure 8 knot, that we're saying everything is dividing and balancing as. So if we look more into those features, and we also look with the 3 bases, the 3 units, because they all have a magnitude of 1, so they're all units, okay? Then what do we see? Well, let's repeat some what we had before. The dilogarithm of the imaginary golden ratio, 4 pi gamma of 5 squared plus GGI times I. All right, so this is our dilogarithmic or our polylogarithm of order 2, and we're using it under this division structure, which takes 6 times to go around the circle, okay? And it gives us a structure that looks like this and this. It's a 2-part structure. One's in the imaginary direction and one's in the real, okay? And these are, at least I hope, familiar numbers, 4 pi, gamma of 5. And I'm wanting you to start to think of gamma as the hyperbolic division function, the thing that breaks things up hyperbolically, okay? So 4 pi is a sphere being hyperbolically divided 5 ways squarely, and that's the real component of this structure. The imaginary component, the orthogonal piece of the same picture, so you could think of this being responsible for this, and you could think of this being responsible for that, okay? But the orthogonal piece is the Giesking manifold. This is great, because we're really interested in the hyperbolic figure 8 knot. And remember, when we take the difference between this and the dilogarithm of the inverse of this argument, we get the hyperbolic figure 8 knot. So let's do that step. We get the dilogarithm of now 1 over the imaginary golden ratio. Using the same rotation argument, but now we're going this way. Notice the symmetry. I could have written that many other ways, right? In fact, I could have written it many, infinite number of ways, right? Because there's multiples of 6 that bring it back to the same value. All right, dilogarithm of the inverse argument has powerful symmetry. It equals to exactly the same here over gamma of 5 all squared minus the Giesking constant times I over here. Great. Now, before I take the difference to get the hyperbolic figure 8 knot, I want to extend what we're doing here to exactly our other units. We have one of our 1 length units, the one that divides the circle into 6 pieces. Let's do it for I, and let's do it for 1. For the dilogarithm of I now, instead of the imaginary golden ratio, so I'm going to compare this one now. Same thing, but put I into it. 4 pi squared over 32 is gamma of 5. Okay, this is a new bit for us, right? So that's the real part. It also is a 2-part thing. Make sure, yep, positive, just like this one. Plus, any guess here?
GGI.
Close.
BFE.
The Catalan constant.
Oh.
Times I. Just like this. Same structure, just times by I with the Catalan constant, which we remember is directly related to the Giesking constant, right? It's a change of argument from pi over 3 to pi over 2. Okay? Look what we just did. Oh. But the thing we want to pay attention to that's new is that here we have a sphere being hyperbolically divided 5 ways and square, but here we have a square sphere also. The top part's the same. The bottom part has 1 part the same. There's 2 of these down here because it's squared, right? Has only 1 of those, and the other one now divides the structure 32 ways. So we have a square sphere divided by 32 ways and the 5 hyperbolic ways. Okay, and this piece, corollary to this piece, has a imaginary component that is the Catalan constant. All right, so was it supposed to be negative? It was. This is supposed to be negative. Let's do it now for 1 over I. That's also negative 4 pi squared 32. So pretty. Minus. I see a lot of symmetry there. Starting to see details of the picture, right? I hope. So we have a dialogistic structure, and we're trying to ask, what does it look like geometrically? What are the rules? We want to know every feature we can about this thing, right? All right. So far we've uncovered 4 pieces. There's 2 more, right? We need to put in 1 and the inverse of 1, which is 1 over 1 is not its actual inverse. It's minus 1's its inverse. So it's a little different in that regard, because if I put 1 over 1, it's still 1. But if I take the dialogism of 1 and dialogism of minus 1, this is positive, 4 pi squared, good start, over 4 times 5 hyperbolic divisions. And this one is, I think, negative. That one was positive. This one's negative, yep. Over 8. Interesting. And no imaginary component. Okay. Kind of makes sense because it didn't have any imaginary component here either. Right? Okay. So we have these 6 dialogrific pieces of our one structure. 6 different ways of looking into the geometry of what this thing is that we're interested in. Now we take the difference. When we take this one minus this one, we get the hyperbolic figure 8 knot. When we take this one minus this one, we get 2 times the Catalan constant. The first one, by the way, this one minus this one is 2 times the Giesecke constant, right? This cancel, we get 2 times the Giesecke constant, I goes away. Yeah, this one, same thing happens, but we get 2 times Catalan. Here, what happens if we take dialogism of 1 minus dialogism of minus 1 equals, it turns out, the log of a very special number, I to the negative pi over 2. Now, why is this exciting for us? For those who haven't maybe been following all the way, or maybe that doesn't pop out right away, what does that play a role in?
A lot.
Yeah, this guy plays a very, very, very heavy feature in quantizing the world. And it's directly constructible. It comes as a piece in the story when the hyperbolic figure 8 is constructed. All right, I might as well go ahead and write that one down. The dialogism of 1 over the imaginary golden ratio minus the dialogism of the imaginary golden ratio, all multiplied by I, equals the hyperbolic figure 8 knot. Okay, so this piece is constructively there when the hyperbolic figure 8 knot is hyperbolic figure 8 knotting. This is really cool. There's a direct connection there. Another direct connection. What's the other direct connection between the inside and outside story?
Well, it's part of our basically hyperbolic Mobius partition equation.
Yep. So on the outside, we are claiming that this is the construction, that an infinite outward reaching inverse construction of this would look like. It would be hyperbolic. And when you take, there's going to be one more modification, but before I do that, when you take this would be an infinite one. We don't want it to reach out infinitely because the hyperbolic figure 8 knot is finite, first of all, okay? But imagine that it's a zero-sized hyperbolic construction on the inside that projects an infinite-sized inverse projection. That's what we're talking about here. So it's like a limiting case, but hyperbolically limiting case. That's what we're interested in. So we're going to set that equal to 0 just to look for the roots of this hyperbolic limiting case. And we find that the solutions, the roots, the x's that would solve this equation are the imaginary golden ratio, 1 over the imaginary golden ratio, the imaginary golden ratio squared, and 1 over the imaginary golden ratio squared. Whoa. Okay, what is this telling you right away?
That's important.
What? This is the rotational argument of the hyperbolic figure 8 knot, right? It's right there. So the roots of this infinite hyperbolic projection of, we're pretending now we had a finite or infinitely small inside projection making it, but now we want to actually match it to exactly this. To do that, we have to go from infinite to finite. We need to wrap something in the system around, right? Get an inversion, get the Mobius connection. When we do that, we need to now modify this equation. We'll go up here. Now we're going to start with the same equation, but we're going to divide the volume here by a circle. And now, instead of saying equal to the zero size infinitesimal that's setting up the structure that inversely, because it's zero size, infinitely projects that structure, okay, which is kind of ridiculous, but that's the limiting case of what we're talking about. When it's quantized, it's not ridiculous anymore. You got a quantized inversion on itself, and it defines the structure scale in which the inversion is playing its role. All right. What we want to do now, instead of going here, where we're projecting all the way out, we want to find the place that this first circle occurs, where we can do this first inversion, and where it's equal to a very specific twist causing the cone hyperbolic internal structure. So on the scale in which the hyperbolic structure is symmetrically making that cone-on-cone structure, we're going to have a very specific size of action to define that, which is this. Okay, and then minus the Planck mass, which is one of the 5 limits in the dimensions of measure. In the total structure, in the cutoffs, we have 5 different Planck boundaries, right? We listed them, I think, before. Planck time, Planck length, Planck charge, Planck mass, Planck temperature. Those cutoffs are cutoffs in the rules of physics. They're cutoffs in each of the dimensional expressions in the built-in connections in the rules of physics. That's where we found them. That's literally how we found them. Those cutoffs exist because they, via their interplay, project 2. Well, you take 1 and divide by the Planck time. And that tells you the number of pieces that the unit that this thing is projected into existence divides up. The unit is the second. So this thing also has units. There's 5 units in the structure because there's 5 dimensions. Each dimension exists as a thing that you can attach a number 1 to, that gets divided up into a different number of pieces under a different action. That's why it's 5 different dimensions. Okay, but they're all compatible in the sense that they all have a 1. At 1, all 5 dimensions agree. They can be fit. Okay, so the 1 in the logic is very, very, very important. But remember, there are more than one kind of 1 in the picture. Here you're seeing 3 at the same time. 3 kinds of 1s in the picture. Beyond the looking into the patterns of all the constants of nature for what kind of simple expressions we can break them down into and undecode them. So we got that entire list going, right? If you can find any improvements, let me know, but if you've looked, you got to admit, very, very intriguing to discover built-in hidden creatures of algebraic geometry writing the rules of physics, writing the rules of how matter gets to play with matter and photons and all the things that matter can do, right? Built in. All right, let's take a look at some of those. So I'm going to turn this screen around. I've organized the most beautiful features of algebraic geometry, the gemstones of algebraic geometry. Okay, I'm starting here. Here we go. So I'm taking we've done this on the board already, the difference between the dialogarithm of 1 over the imaginary golden ratio and the dialogarithm of the imaginary golden ratio, times it by I, we get the hyperbolic figure 8 knot. If we go up in power, remember we have these power roots over here, square and 1 over imaginary golden ratio squared, that were also in the story. So if we do that here, if we just square our operator here, okay, we square the argument, then the exact same structure gives us 2/3 the hyperbolic figure 8 knot. All right, another built-in boundary. And how do you get to that boundary? Both of the rotations in the structure have to be squared. Okay, and let's do it again. Cube it. We just step up by making a 2 go to a 3. 2 goes to a 3. And we can get now 0. Okay, so there's a repeat of this. Powers of 3 will give you 0, right? Okay, so over and over and over, there's going to be a repeating of this as we go up in powers, right? There's another direction to move in this structure. You can go up in higher rotations by counts of powers. If you do, you're going to return this structure over and over. So there's a modular structure built in. Great. Now, let's go a little step further to recap what we were saying before. If we use I instead, we get 2 times the Catalan constant. If we go up in powers to squares, it goes to 0. It only takes 1 step to go to 0, and it does it every other time. You go up again, you're going to get, I think -2, okay, and over, back and forth. All right, here, if we step up, we're not multiplying it by I, because I'm just add another I there, but this is the interesting feature for me. There's other ways to write these, which is the point of kind of what I'm saying. Here's the interesting features that I've found and the simplest connections between them. I'm trying to write them all in similar uniform ways, right? So if you take the log of I to the I to the negative pi over 2, notice there's some sort of relation happening here. They're different, but here we're taking the natural log and here we're taking E, which is, if you take log of E, it's 1, right? So there's some sort of relationship here, and they're all connected to one of the most famous equations there is in mathematics, all of algebraic geometry, right? All right, let's move down the list. I want to just expose you to the beautiful features that we got here. Not just e to the pi I equals -1, but we have a lot of other important ones, okay? We have -1 to the 1/2, -1 to the 1/3, giving us our 2 rotation operators, but we also have 1 and -1. Okay, we've covered a couple features last time when we focused on, I think, the imaginary golden ratio. The one thing we didn't show was the symmetry in this regard. I think I showed the golden ratio plus 1 equals the golden ratio squared, and then the golden ratio minus 1 equals 1 over the golden ratio. But didn't show the comparison with the imaginary golden ratio. So here it is. Imaginary golden ratio plus 1, same structure, is, instead of being squared, it square roots the imaginary golden ratio, but first it triples. If it wasn't for the 3, it would be exactly the opposite. Interesting. But the other one is exactly the opposite. It's the same structure as the golden ratio, the imaginary golden ratio minus 1 now, just like the golden ratio minus 1 was 1 over the golden ratio. This one now is -1 over the imaginary golden ratio. All right, so a lot of constructive symmetric relationships built in. It's not just a random set of beautiful relationships, they're symmetric to each other. All right, we covered golden ratio in terms, I didn't write it this way before, in terms of square roots of 1. I think I only showed in square roots of 1 squared and so on. But in terms of 1 or -1, we'll get the golden ratio or the imaginary golden ratio in an infinite nested series of square roots. In one case, we have arguments of 1 in every single element, just 1, 1, 1, 1 all the way, and we get the golden ratio. Just like when we get the golden ratio from the continued fraction with all 1s as elements. Nice clue. The imaginary golden ratio, if we do all -1s, we get it. Great clue, but also a nice relationship between the two. Now, if we go up in power, if we think of these elements as being higher power things, then the imaginary golden ratio can be thought of as an infinite nested radical set of 1 squared. 1 squared has a lot to do with E. That's really beautiful. We'll get there, I think. But now, as the same corollary here, the imaginary golden ratio is I squared. So this makes every element turn into -1 again, the same as before. But this is a way to look at it with a higher dimension in the arguments. Again, this relationship of rotational rule between the three, I, the imaginary golden ratio, and the golden ratio. But there's a whole bunch of recursive relationships built into these constants themselves. An infinite set between powers of the golden ratio, and likewise an infinite set of powers relating the imaginary golden ratio. Same exact rule, except we just change plus to minus, like we do almost every time, or we change a 2 to a 3. You can get any Fibonacci number. You want to get the 112th Fibonacci number, the 6 millionth and 7th, put that number in here, and in order to get the answer, you would put the golden ratio raised to your number minus negative golden ratio raised to negative your number divided by the square root of 5, and it'll give you your Fibonacci number. Okay, so the whole Fibonacci sequence is golden ratio set or golden ratio inversion balanced is a way to see it. So here's another prescription between the Fibonacci numbers themselves. See the limit between each successive number. If you divide this number by the previous, as you go further and further and further in that construction, goes exactly to the golden ratio. All right. Here, we mentioned this super golden ratio and the golden ratio's infinite factorization structure. Here, the super golden ratio infinitely factors all of its inverse powers into 3 copies of itself, into a cube. This one infinitely factors into a square. Really interesting. So beautiful relationships there. That one's a new one compared to the rest of the set. This has been the same golden ratio the whole way through. The rabbit constant, it's a summation of powers of 2 golden ratio related, and then you take the floor. So every time you step up, if there's a remainder, you cut that off. Interesting. This is a zeta of 3 multiplied by 2, gives us the same thing as the summation of all the harmonic numbers over n squared. 2 to the n, any power n, is the same thing as, this is n choose k. We're going to take the summation of n choose k from 0 to infinity. So there's a partition way of talking about these powers of 2. Okay? The CPA is a Paris constant. It's the rate at which the golden ratio is approached in the continued fraction form. And look, it depends on the golden ratio. Fibonacci factorial constant depends on the golden ratio squared. Right? This is the Lucas number and the Fibonacci numbers. So all the Fibonacci numbers can also be written this way in terms of a sum, or the Lucas numbers, which you might note are very related to the Fibonacci numbers. In fact, the Lucas numbers, you could argue, are more related to the Fibonacci numbers than the Fibonacci numbers. It's a crazy statement. Let me show you what I mean. So the Fibonacci number is composed of all of the sum of the Fibonacci numbers, inverse Fibonacci numbers. So it's got all of them in there. But the Lucas numbers have all the inverse Lucas numbers, but it turns out that's equal to all of the Fibonacci numbers and all of the double Fibonacci numbers. So it's got even more. It's got all the copy of all them in there, same number, whole set, and another copy of Fibonacci numbers in that set. Anyway, this is simpler, but yeah, it's got an extra copy going on there. Here's another. Red n is, remember, 5. So 1 over the golden ratio plus the golden ratio gives you the square root of 5. This is really cool to notice these connections and things, right? I mean, you might think of, oh, the logarithm. Logarithm of 7 is what? It's going to be a crazy number, not an easy number to state, right? And it goes on and on and on, and it's irrational. And cosine, hyperbolic cosine of 7, at least but together, multiplied by 7 comes back to a whole rational number. Right, n squared, or 5 squared. So we have 3 different ways of arranging our 5. Our 5 different dimensions, right? So one way we're square rooting, and it's the golden ratio that's doing that job. One way we're squaring, and it's a hyperbolic structure, both the natural logarithm and the hyperbolic cosine, that are doing the job. Both of them are using 7 to do it, though. Now, this is very similar to this. We switch from hyperbolic cosine to hyperbolic sine, which is interesting because if you have the hyperbolic cosine, you should also have the hyperbolic sine. So same structure, but then yields n squared to being just gamma of n. So these are 3 fundamental ways for our 5 things to be under a balance. They can be under a square balance. They can therefore be under a square root balance. Those come together, right? But you can also be gamma of 5. You can be under the gamma balance. You can be hyperbolically dividing, right, via the way the gamma function orders and structures things. Okay. Here's a big step for us. We started this, well, go to the top. Here, in our dilogarithmic structure, the real part, complementary to the Giesecke manifold itself, is this 4 pi, a sphere, divided by gamma of 5, or a sphere hyperbolically dividing 5 ways squarely. That same piece is equal to the radius of the neutron divided by the radius of the electron. Okay. Now, we don't know those to extreme accuracy. So you might think, that's a coincidence. That's fine. Notice, remember, this piece has corollary pieces. The Giesecke manifold comes with also the Catalan constant. Okay. Well, the Catalan constant is equal to the radius of the neutron divided by the radius of the proton.
Yep.
Okay. Both of these constructions come together, and both of them divide things up. Look at the miracle here that they're dividing things up in the same scale ratios that the neutron, proton, and electrons radii are supposedly doing.
I mean, that's a very...
That should make you more interested in trying to find the symmetries. We're finding connections in the world. These are only known to certain accuracy. 4 pi, gamma of 5, we know those numbers really, really well, right? Those are only known so well, but as well as we know them, that's true. And the other relationship between the 3 gives the other relationship in the structure. It's a really nice arrangement. Now, that doesn't finish the story for you. That's supposed to be enough to say, wait a second. There's a partition construction that defines the hyperbolic figure-8 knot that at the same time constructively defines 2 other expressions, right? 2 other unitary expressions in the same construction, of the same construction, and the limits built into those constructions carve up a domain with the same proportions as the proton, neutron, and electron. Now, that's really interesting. That's a great start. Okay. Let's investigate that little line further. Yeah, let's do both lines of these. Okay, so Catalan constant is K. Remember, if you're investigating this and keeping along, you might have a different representation for that one. The rest of these are pretty uniform representations, but this one's all over the map. I'm going with K for now because the other one that's common is capital C, and I have a lot of those. So Catalan constant. Here's the domino tiling constant. Now, just doubling both of these, we can see that there's a relationship between them. Okay. Now we should be interested in the domino tiling constant, the dimmer constant, the logarithmic connection that's built into that structure. And we have a story of that structure that divides the world the right way from the start here. Let's follow it. Let's see what other features we can follow from this structure. Now, really what we're really doing right now, other than the connection here with the neutron, proton, electron, for the rest of this poster, I'm really going to be sticking to the features that just found from algebraic geometry. The connections found from people studying the rules, from when you map things and find their relationships and characterize and classify their relationships and start the conversation about what those relationships are doing. It leads to this whole algebraic geometric structure, a discovery of all the structure. Okay. Gamma function symmetrically balancing on the golden ratio, the unitary action. The imaginary golden ratio symmetrically balancing in the inverse way. Okay, and it has 2 ways of doing it. The gamma function does it this way on the golden ratio, does it these 2 ways on the imaginary golden ratio. The Catalan constant, gamma function constructed from 1s and x's again. Okay, so another way to put together things also in the story. So I'm just wanting to get familiar with the numbers that are important in this hyperbolic division construction. All the numbers we found are really hyperbolic rules. Okay, here's a really beautiful one. This number here, called the Euler-Mascheroni constant, is equal to negative the first prime, the first derivative of the gamma function at 1. So the gamma function at 1, what's its derivative? What's it doing there? What it's doing at 1, inversely, is whatever that thing does. Okay, well, let's look at what that guy does. There's, turns out, lots of stories, lots of ways to talk about what that guy does. Here's one. As we approach the limit, as n goes to infinity, of the difference between breaking up the hyperbolic logarithm into a whole number of steps, where you always have to step a step of 1 to 2 to 3 to 4. You can't step less than that. To step size approaching 0. That's what the integral is. It's infinitesimal step size. So step size of 1, we start at 1, we go to 2, 3, 4, 5, and this one's infinitesimal. So the difference of mapping that function in quantum steps of 1 to infinitesimal steps is this number. And let me give you a picture of exactly what I was saying there. Right here, this picture. Here's a graph starting from 1, out to 12 and cut off to there, of 1 over x. Y equals 1 over x, the hyperbolic logarithm. Okay? And we can graph it crudely by stepping in steps of whole one number, right? From 1 to 2, 2 to 3, 3 to 4. So if we do, it chunks it up like this. That's the graph we're making. All right, as we step out further and further, the graph gets closer and closer to the red graph. The blue graph and red graph get similar. But there's going to be a difference. If we sum up the whole difference of the blue steps sticking above the red, that value in that graph becomes the Euler-Mascheroni constant. All right, so we're really interested in that number also. It's built into the hyperbolic structure of reality. This is the natural log of 1 over x dx from 0 to infinity is the Euler-Mascheroni constant. It's built in to the hyperbolic structure of reality. So there's a clue. There's something quantizing and something smoothly fitting things together in the same story. That guy plays that role. All right, other ways to represent it. 1 over log 2 is an important one in construction, and it's equal to the infinite integral, or is from 0 to infinity, of 2 to the negative x dx. 1 over 2 to the x. Okay? These are two beautiful ones, but you might not have, well, you've heard of the zeta function. It's really famous. The Riemann zeta function has a first derivative at 0. E to the Riemann zeta function's first derivative at 0 is 1 over the square root of 2 pi. If you do the same construction, but you put in the beta function instead, take its first derivative at 0, now it's s over the square root of 4 pi. And s, remember, is the arc length of the unitary lemniscate. Let's look at it real quick. All right. Unitary lemniscate has this equation. That equation has built-in features that come with it. That relationship fixes rules like the circle has a fixed radius or radius to circumference relationship. This has a fixed relationship, right? Several fixed relationships that it fixes. All right, so this lemniscate goes to 1 and negative 1, has an arc length all the way around. You start right here, say, go all the way back to there. That total length is what we represent with the letter S. So we're going to look real quickly, but half of that is L, quarter of the whole length is L1, and L2, we'll get there. Okay, so hopefully these guys start to become a bit familiar friends, but let's go there. S is 2 times L, because there were 2 petals, right? L is just 1 petal, S is both petals. Oh. Okay, it's also equal to 4 complete elliptic integrals, or 2 times pi multiplied by Gauss's constant. Okay, if you've never heard of Gauss's constant or elliptic integral, or say a lemniscate constant, these are friends you want to get familiar with. They're, first of all, very pictorial and easy to understand them the same way that understanding pi can be understood, right? So you can get a geometric understanding of these guys, but they're making a very simple interplay, right? L2 is just pi over s. L1 is s over 4. They're very simple structures of something dividing things up. Oh, he's so cute. All right, here's one I want to stop at. If we take all of our lemniscate constants, L, L1, and L2, and divide it by S, we get 4 pi over 32.
I've seen that before.
Yeah, that's really interesting. Wait, if we take all the lemniscate constants and divide it by S, the full lemniscate constant, we get 4 pi over 32, which would suggestive of a sphere being divided 32 ways. We saw that at the top, right? Did we see any of those? Yeah, we have 4 pi's and 32. Oh, but here it's 4 pi squared over 32. It's half the story over there. Interesting. Okay. Let's also look a little further down. Zeta. Where did it go? There it is. Okay. The zeta function has an interesting symmetry built into it. So setting the zeta function equal to the zeta function with this argument in respect to 1, and the arguments were inversed, but it turns out because tangent and cotangent are inverses of each other, I can write them without the inversion here, right? So tangent of something plus 1 in the zeta function is equal to cotangent of something minus 1 in the zeta function. Okay, that something is 4 pi over 32. And you can write it this way also. So it's got this symmetry both ways in relation to 1 in the zeta function. Now I remind you, in relation to that conversation, we have the gamma function that was in relation to the golden ratio and the imaginary golden ratio in these symmetric ways in relation to 1. Okay? So we're talking about a system that's dividing up a sphere in different ways. Well, from different angles, it divides up in different ways. So we're looking for the symmetries of those ways. So we want to know all of what its ingredients really are doing. Remember, the length of the sine wave, or the unit wave, is equal to 4 pi over s plus s. So our lemniscate constant, our lemniscates are built into the story we've always been telling, right? Into the unit circle already, the lemniscate constant can't be taken out because you can break up the unit circle into sines and cosines, and the sine has an arc length. The sine wave has an arc length, and the cosine has an arc length. They're equal, but they're both equal to this. Can't get away from our S being part of the story, so we should get familiar with all of its beautiful symmetries. Here's some more. E to the pi, now that you know what this S is, this lemniscate constant, it's up there with pi, exactly as important as pi, okay? It's a geometric number, but of a unitary lemniscate, not a unitary circle. S to the 8, the lemniscate arc length to the 8th power multiplied by the Weierstrass constant, Weierstrass, how do you say that? Weierstrass, the Weierstrass constant to the 8th, both of these are the 8th, divided by 8 squared. 8 plays a role 4 times. All right, once, twice, and twice here is again e to the pi.
It's very interesting.
So this is suggesting that the construction of all the even hyperspheres have this division structure in them. They depend, they can be, this isn't an approximation, this is exactly, okay? So they depend, that structure can be written as a dependence on the lemniscate and the Weierstrass fractal, the simplest fractal. That's really interesting. Okay, so this is connected directly to that. This is a perfect match. Now you can rewrite it like this, in terms of lemniscate instead of S. Okay, now here's a step. E to the pi, here everything's squared here from here. So this was 4, it got squared to an 8. This was 4, it got squared to an 8. This was 2, it got squared to a 4. Everything was squared. So I to the negative I squared, I think I erased it already, right, is e to the pi. All right, I could pull the negative I in there to make it the same as that one, have just to the power of positive pi over 2, but here we'll write it I to the negative pi over 2 to match the way we're doing it elsewhere. Look what it's equal to.
Oh, the thing's gone downstairs and now we got 2 pi.
Yeah. Okay, these are all constants that we can tell stories from. These are all constants that are giving us information, right? S, 2 pi, very related to begin with, but S to the 2 pi, the Weierstrass constant to the 2 pi. So there's circles playing some role here, 3 of them, and this one gets square rooted twice. All right, there's a different way to connect these things, but they're not approximations. These are identities. So if you're using this ingredient, which we do with the hyperbolic figure 8 knot, then you're using this structure somewhere. So we're going to be interested in these characters. And let's look at a few more ways to represent them. It's really beautiful. This is really beautiful. That one. Let's go to this one. The log of I to the I to negative pi over 2 square rooted multiplied by 8 is 4 pi. It's a whole sphere. A sphere is made out of 8 of these square roots. Wow, that's a nice connection. I mean, connecting the powerhouses is the ones we're most excited about. Any connection between pi and any other player that's on the level of pi, like the golden ratio, the imaginary golden ratio, I, the list we've been playing with, is a really cool thing. This is going to give you insight into actual prescription of structure that exists. Okay, the zeta function, again, has a way of limitingly approaching the Euler-Mascheroni constant. The gamma function does too. And the digamma function does too. Now, it's also true that the Euler-Mascheroni constant relates directly, we mentioned this one before, the sum of all these gives us the total volume sum of the even dimensional hyperspheres, and it equals e to the pi. Okay, what the Euler-Mascheroni constant is also directly related to the whole construction of primes. This is a giant clue. For anyone interested, really look here. The prime construction, the entire product of 1 over 1 plus 1 over p prime set from 1 to n, okay, as we go all the way up, and we let n go to infinity, multiply the whole thing by log of the prime n, that thing equals pi squared over 6 e to the Euler-Mascheroni. The Euler-Mascheroni constant, which remember tells you the difference between quantizing the hyperbolic logarithm and infinitesimally breaking up the hyperbolic logarithm. Okay? It's playing a role in the construction of the whole set of primes, logarithmically, but the whole set. That's not, I mean, it approaches as it goes to infinity, but it gets better and better and better and better and better. Okay, also, here, I just changed plus to minus. Everything else is the same. And now it's even more simply related to the Euler-Mascheroni constant. Okay, so this is a powerhouse. This constant is holding huge secrets about the hyperbolic construction of reality. It's built into the basic rules of primes themselves, of logarithmic structure itself. Okay, it's a very interesting constant. It's there with pi and e and I. Okay, I hope you really get excited about these constants. If some of them are new to you, they should lead you down a wiki hole or hopefully a Wolfram hole for weeks, months, hopefully for the rest of your life. Right? The Wolframs really organize things well, so it's fun to follow the clues there. Here's another interesting clue. If we take all the primes squared plus 1 divided by all the primes squared minus 1, meaning we start with the first prime, do that, and then we multiply that answer by when we do it with the second prime, and we do over and over and over, multiply all those answers together, we go to 5 over 2. The primes related to the Euler-Mascheroni constant are also related to 5. 5 plays a role for some reason. This is cool. I love following clues like this. First, I want to thank our intern. He's also a supporter, and he's been here for most of the year and committed to doing this with us. And together we have really discovered a lot. He's asked me so many questions that I didn't think of, so it's led to all kinds of things. He's discovered things, right? More than one of those constants on there from ones that he found before I ever found. So he's playing a wonderful role here at the Physics Monastery. And this year wouldn't have happened without him. So thank you very much for this year. I think we've found very valuable information that I hope one day changes the world. So I think it was very much worth it.
Thank you.
Yeah. And also, I want to thank Wayne Eskridge recently supporting us, and all of our supporters here, that this wouldn't have happened without. Okay, so I just really want to throw these names here and thank everyone here for the contributions they've made to the discovery so far. And let's also mention NIST and CODATA and Wolfram Alpha, because without the data set and without a power tool to organize and try to explain that data set, we would still be stuck at not asking these questions, right? Not properly, not coherently, and systematically. So these are very significant players in the story we're uncovering. Let's look at some more of the cool clues in algebraic geometry. Smaller, there we go. Continued fractions. The golden ratio again has a continued fraction, so we're interested in continued fractions in general now, because we're really interested in the story the golden ratio is offering, and we know that story is part of the structure in the ultimate story. The inverse golden ratio is almost the same thing with the first element goes from 1 to 0. Ramanujan's first continued fraction constant uses the same structure, but instead of 1's up top, we now do multiples of 2 pi, e to the negative 2 pi, and we're still 0 on the front there. Pi over 2 has many ways to be written. Here's what I think is one of the most interesting. All 1's up top, 1 at the first element, and then we do 1 over 1, 1 over 2, 1 over 3. We do all the simple fractions. This division algorithm is extremely simple, and it gives us pi over 2. Here's another extremely simple one. All the bottom ones are 1, and the tops have 2 in each. 1 times 1, 1 times 2, 2 times 3, 3 times 4, 4 times 5, and onward all the way down. Also gives you pi over 2. Compare that to the lemniscate divided by 2. These pi and the lemniscate constant have a lot of marriages, a lot of intersections that they define each other with. Here's another connection you can make. So instead of the bottom being all 1's, L over 2 has 1 and then all 2's. And instead of being 1 times 1, 1 times 2, 2 times 3, we start out 1 times 1, then we go straight to 2 times 3, 4 times 5, 6 times 7. So we're going up in number. We don't repeat any numbers, except for the first 1, 1. Okay, another really interesting continued fraction, comparison to these three, is 2 times the Catalan constant, which remember was one of our superstars in our structure. So the 2 times the Catalan constant, what is it? Let's compare first the bottoms. We have 1, 3, 1, 3, 1, 3, on and on and on. What is that in comparison to pi over 2 and L over 2? Well, here, starting from the second step, 1 plus 2 is 3. And then 2 minus 1 is 1, and 1 plus 2 is 3. So we get the difference in sum between the ones above, and we repeat the whole bottom. So we can repeat this structure pretty easy from these two. What about the top? Top is 1 times 1, like all 3 of these started with. And now we go 1, 2, 2, 2, 3, 2, 3, 3, 3. We repeated 2, 1, 2, 3, 4 times. So we're over-repeating things. Interesting. They're all different constructions of repeats telling similar stories. And they're all powerhouses in geometry. Right? Great. Catalan by itself can also be, not 2 times, it's just Catalan this time. Another way to write it, in terms of powers of 4. Start with the first one, 1, and then after that it's 1 to the 4, then 3 to the 4, so they're all odd, 5 to the 4, 7 to the 4, 9 to the 4, 11 to the 4, right, all the way down. But the bottoms start out as 0, and then 1, and then 8, 8 to the 1, or 8 times 1, I should say, yeah. And then 2 times 8, 3 times 8, and so on. So multiples of 8 in the bottom, powers of odd numbers on the tops. 4 times, 4 power of odd numbers. All right, another number that's incredibly related to the continued fraction form is e, the hyperbolic base of logarithms, right? The hyperbolic number even. And e is 2 plus on top we go 1, 1, 2, 3, 4. We just keep going up. On the bottom we started with 2, but then it's 1, 2, 3, 4, 5. Keep going up. Or, I like this one the best, 1 over 1 minus e. 1 over 1 minus e is equal to 0, 1, 2, 3, 4, 5, all the way down. And on the top, instead of starting at 0, we just start at 1, 1, 2, 3, 4, 5. That is one of the simplest ones you can state, other than 1, 1, 1, 1's all the way down. And it's 1 over 1 minus e. Now, real quick, zoom out a little bit here. 1 over 1 minus e probably shows up. Oh, look at this. 1 over 1 minus x. Put an e in for x. What happens? E to the n. E to the 0, e to the 1, e to the 2, e to the 3. Counts of all the powers of e, right? Here. All right. I'm just trying to draw a little bit of connections there, but let's continue with continued fraction. So e itself, the hyperbolic number, is related to the continued fraction form in a simple countable way. Great. A simple programmable way. Tangent, the function of tangent, if you want to give me an argument for tangent, I can put the x in there, and we can make its continued fraction by then just taking that x and squaring it all the way down here and doing this with the minus signs. Yeah, I might need to write minus on that one. That might be a typo. Okay, so Ramanujan also has another form of continued fractions that are power-based here. Starts out with 1/5 power of whatever that base is, the q, and then it goes in whole counts after that. And look how simple it is in the bottom. Great. Square root of 2 and square root of 3 also have simple representations. And remember, the square root of 2, or square root of 3 over 2 is just the distance between the smallest 1 by 1 by 1 triangle. Right? Peak to bottom is a square root of 3 over 2. Okay. Let's start from these clues. If we take the entire sequence of numbers, starting from even ones on top, divided by odd. So the first even number divided by the first odd number, 2 over 1. Multiplied by the second even number divided by the second odd, 4 over 3. And on and on and on and on all the way down. As we do this, we start out with a number that's 2, and then it gets a little bigger than 2, and it gets a little bigger than 2, and even a little bigger than 2. And it keeps going, right? But it's getting bigger and bigger. It gets bigger or smaller by a less and less amount, because each number is less and it's closer and closer to 1 as we go out. Each number is approaching 1. So, but because we're multiplying them, that means they always get bigger and bigger. It never gets smaller, because each number is always going to be a little bit bigger than 1. Okay, so it's an infinite set. That means this thing has to go to infinity. Okay, very famous thing proved in math. I think it's a fun thing to play with. But let's look when we do the inverse. Let's keep the tops all the same and get rid of the 1 and move all of the bottoms over 1. So that now that everything is slightly less than 1, but going to 1. Okay, the simplest, closest thing we could get. When we do that, it goes to 0. Okay, so we have two limits, infinity and 0, from this construction, this product construction of all numbers. Here's a really interesting step. If you take this one and this one together, right? So 2 over 1 times 2 over 3. You're going to take them at the same time. And now we're going to multiply 4 over 3 and 4 over 5. Well, and we're going to keep going. Let's just take infinity and 0 together. And we get pi over 2. If you take infinity in this construction, which is pretty easy to see why this is infinity, this one's pretty easy to see why it's 0. And when they're both very similar to each other also. So put the structures together and zip them together in infinity, and it goes to pi over 2. If you zip them together 1 by 1. Right? Now look, what's the difference here? We're taking 3 halves, which is, we flipped this one upside down. And then 4/5. We kept this one. And now 7/6. We flipped this upside down and kept this one. So we're doing everything along this row, but we're flipping every other one. And when we do that instead, we get the lemniscate constant over 2. And they both can be constructively written down in very similar forms, right? This is an infinite product from 1 to infinity, in both cases, of 1 plus 1 over n, or 2n, right? to the same powers, -1 to the n plus 1, or -1, doesn't matter. It gets the same thing. Here's the difference. These things are completely the same except this doubling here. And that plays out to be a 4-piece construction that differs like this. All right, so I'm hoping you're seeing there's a relationship between pi and the Lensgate constant. And the relationship's telling us a lot. Here, it's telling us a constructive form that goes off towards infinity, whatever infinity means, but it's sailing off constructively, piece by piece. You can keep adding another piece in the division structure. Okay, moving up. Here's a lot of famous discovered constructions in math, right? If you take the sum of all the square numbers, all the way up to n squared, if we cut it off somewhere called n, pick some n, that's where we stop. No matter where we picked, it's going to be equal. That sum will be equal to if you just take an n times n minus 1 times 2n plus 1 divided by 6. So the sum of the squares have a structure in them. They have a summed structure that's equal to this 3-part thing divided by 6. It's just there. The cubes have a different feature. They have a summed feature that's equal to the reduced sum, so no powers now, all added together, and then squared. Interesting. A lot of symmetry showing up in groups of things. Now, note, this happens no matter what number you pick for n. You have to pick a number. I mean, you can try to pretend it goes to infinity, but if it does that, then you're not going to get anything but infinity, right? But for any number you pick, this structure matches until you get the numbers that don't make sense. All right, we saw before the zeta function's got some balance around a tangent or cotangent structure of 4 pi divided by 32. Zeta of 3, let's start right here with zeta of 1 is equal to 1 over 1 plus 1 over 2 plus 1 over 3 to infinity. Okay, it equals infinity. But zeta of 2, you just square the bottoms. That's all we changed. And now instead of going to infinity, we went to pi squared over 6. Zeta of 3, we're doing the exact same thing again, but we've cubed all the bottoms. And now we go to zeta 3. We go to a number that we know this way only. Cool. Makes you interested in the number. Well, I shouldn't say we know it that way only. Here's some other ways we know it constructively, right? I just couldn't write it in terms of pi. So it's logarithmically known in terms of the construction of logarithms. So the integral from 0 to infinity of log of x and its symmetric log of 1 minus x divided by x in 1 minus x dx times by 1/2 is zeta of 3. Pick any, well, I mean, over all x. So in this in the logarithmic structure, hyperbolic structure, this form gives you that value. So it's a form relationship. So all these things are relationships building and telling you a logical form. Learning to understand the form is the goal here. Let's look at zeta 3 has two other interesting ways. Another half, but this is x squared over e to the x minus 1 dx. Very, very, very hyperbolic, central. And this is 2/3. We're both going 0 to infinity both times, but 1/2, 2/3. X squared, e to the x minus 1, e to the x plus 1. 1/2 and 2/3 is all that changed with the plus and minus. And they both will give you. So there's two similar ways to get here, is what I'm pointing out. There are many more. I'm trying to get the most beautiful, simple ones. Here's another 2 pi squared over 32 in our relationship to a Catalan constant and the Madelung constant. Actually, this is a nice one to see. 2 pi squared over 2 times the gamma of 5. A little different than before. I want to go to this. Here we go. I ended here before on the beta function. Let's look at these integral hyperbolic constructions. We're taking an integral from negative infinity to infinity, so over the whole space, of e, our hyperbolic base, to the negative x squared. Okay, like a familiar, okay, dx, to the whole thing. Now, yes, this reduces, right? This reduces the square root of pi. But I'm writing it in symmetric form to the ones that come below. So let's look at this. It equals the square root of 2 pi times by, inside the square root, another square root of 8 over 32. All right, we're going to now cut off, instead of from negative infinity to infinity, we're going to go from 0 to infinity, and we're going to bump the power up to 4. Okay, that's all we're changing. And now we get a different geometric construction, giving us a clue about what the hyperbolic space does all the way from 0 to infinity. We get the square root, again, of the lemniscate constant divided by 8 instead of 2 pi, and then another square root inside the square root of 2 pi. It moved inside. Okay, cool. Now let's just change the 0 here to negative infinity, so we go over the whole space of the same structure. That's all we're changing. And we get this. Okay, these are huge clues about the structure of hyperbolic geometry. Okay, more integrals relating the universal parabolic constant with pi. See the relationship here? 1 plus x squared dx, but here we're taking the square root, and here we got 1 over 1 plus x squared, and the limits are completely different. Negative 1 to 1, negative infinity to infinity. And it gives us a cousin to pi. Pi is the universal circular constant, and pup is the universal parabolic constant for parabolas. Right? Built into the structure of all parabolas is one form given by that number. Built into the structure of all circles is one form given by that number. Given the relationship between the radius and the circle and the circumference here, this is given a similar relationship but turned inside out. Okay, more relationships between the lemniscate constant and pi. But here's an interesting one. L over 2 and L over 3. Okay, what's the difference? We're taking an integral from 0 to 1 in both cases, dx. And in L over 3 case, it's a square root of 1 minus x to the 4th. In this case, it's 1 over that. The inverse has a relationship with itself. Okay, hopefully, if these are clues you've never seen before, these are prescriptions of algebraic geometry or rules that define these characters of geometry that you've never seen, hopefully you're being overwhelmed by how this is written into the rules of calculus, right? The geometric form, the numbers we're pulling out here that tell us something about a lemniscate or a circle and so on, they're coming from the rules of calculus. They're built into the structure of calculus. I'm hoping you've seen that rule. I mean, just leading to that. Okay, that's one of the reasons it's really, really exciting. Now, let's get to we have lots and lots and lots of really cool rules. I'm going to put the whole poster available for people to get online. Let's look at some of these quickly. The zeta function has simple, easy ways to get to an argument of 2 pi I, or a result of 2 pi I, or negative 4 pi. So if we're interested in how we're dividing up circles and spheres, here's a prescription in relation to the zeta function for doing that. Here's deriving gamma function and some simple relationships built into the gamma function, and corollary ones, the beta function. Note, pi and s in the beta function are very similar again. The only difference is instead of being half and half for arguments, it's half and a fourth. We're splitting in 1/2 in one way and 1/2 in another way gives us pi. Splitting in half in one way, 1/4 another way gives us s. So these two are really related again. Lots of relationships built in between beta function expressions, gamma function expressions, zeta function expressions, and so on. But the numbers that are kind of going to be familiar here are 8, 18, 32, being the 7 and 5 together make 35, okay? 18, 32, there's a 32. These things are showing up all over the place. Where do those divisions come from in the story? We think, ultimately, it comes down to the 5 hyperbolic divisions that are defining the Planck constants themselves. Okay? So these are the 5 ways we're hyperbolically dividing what we're calling the minimal arena. Okay, the minimal arena internally is the hyperbolic figure 8 knot, and externally the n sphere and the hypersphere of maximal volume. But it has 5 hyperbolic ways that are interfacing together in that construction. And each of those, this one's, zoom down a little bit, the derangements of 5, red is 5, red n is 5, derangements of 5 things is 44. 7, blue B is 7. 7 times 5 is our break and scale symmetry, so we're taking our 5 things now and scaling it up on another scale by 7. So 44, 35, this is internal, this is in and out really. But then external only are these three options, which have a very similar relationship. And note that 3 is take 44 minus 35, square root it. So these relationships are related to the inside, but our expressions outside for the Planck constants, the degrees of freedom available to each of those different Planck constants are 44, 35, 18, 8, and 32. Here's the equations that define breaking up into those different numbers of pieces. Here we break up into 44 pieces this hyperbolic way. And that's the rotation. The number that this division defines is the rotation that allows you to do it. Here we're breaking up in 35 ways in a different hyperbolic way, and we have rotate a different amount to do it. Same thing over and over, a different hyperbolic way of breaking up, and we're rotating a different amount to match, and so on. So these equations allow us now to define these rotation amounts to any value, and we know that they apply to limits of something that breaks up 44 ways. This one applies to a limit of something that breaks up 35 ways. This one's 18, this one's 8, and 32. Okay, so we have rotations that have relationships to a number of pieces under those rotations. Great. If we take those rotations, we can solve for them now, and here's the first digits. The 0th one, the first, second, third, and fourth. All 5, I call the first one the 0th, right? We get these numbers, which strikingly, for the first few digits, perfectly match the known digits in the Planck constants. And if we take all of those rotations, assume they defining a base that's double covered under that structure. And we want those rotations under that double cover to be all balanced together, but they're going to be raised to whatever number that they're dividing things by. 1 over that number of things is how many things you're breaking up that way, right? So dividing, but the other one is a projection only, so it's positive, okay? Same rule though. We're going to take all the rotations, multiply them by a double cover of that division amount. So we breaking the whole structure, all 5 of them now, into many pieces, right? But these pieces are under this rotation and these are and so on. When we do that, we get numbers under bases that perfectly, we can go as many digits as we want now under this, okay? And project how many digits we want for the rest of the structure of these constants. That's our assumption. These are the hyperbolic ways that all 5 boundaries are dividing against themselves in the structure, okay? When we make that assumption, we get the Planck constants to all the rest of these digits that these equations define. But that gives us the ability to now define the exact forms and limits of the exact bases under this projection. There's 5 bases, 5 ones being put into the story that are being broken up different ways. This tells us how they're being broken up exactly. Every one, every base defined in the structure from these 5 numbers alone. Great. There's our start. We're going to use now all of these constants to then put together to get other arrangements, other relationships, other geometric algebraic relationships. Before we do that, we need to remember our hyperbolic structure, which we did bring up here. Yeah, so our hyperbolic Mobius equation for how the outside structure of our hyperbolic figure eight knot is expressing and wrapping up on itself. So it's expressing exactly as the hyperbolic figure eight knot expresses externally, but it takes those parts in one way and wraps it so it doesn't go out infinity. It's it's a finite construction, and its rotational inner gears are made by the hyperbolic figure eight knot's limited structure. And we have a scaling parameter, which is picked by the Planck mass for the mass gap. In our hyperbolic structure, when we zoom into the right scale of the hyperbolic structure where this extra square symmetry comes in, then we get our cone-on-cone structure, we get our single-sheeted hyperboloid, we get the double-sheeted hyperboloid, and we get our torus. Okay, so the cone on cone, the charge boundary. That's the division in the hyperbolic structure that we're calling charge. It has a certain scale, a certain built-in fixed relationships, and so on, but that's the one we're calling in this division structure the charge division. Okay, this one right here is temperature. This one. And this one's the mass gap. So this one's mass, leaving this one to be space. And that's different than before. I think I put space here and mass there. So we're swapping those in the story. The mass gap's the one that's the mass boundary, and the space is the one that's picking up the toroidal structure, which is building in all the rules of Clifford-Torres rules, or Clifford algebra. When we zoom into the scale of 10 to the negative 7, right, our symmetry scale. Planck mass gives us the scale and the gap between the upper bowl and the lower bowl. And when we use this hyperbolic structure with that Planck mass gap, we get exactly a division structure now that's quantized, but instead of having its roots be the imaginary golden ratio, 1 over the imaginary golden ratio, and both of those squared, we get 4 different roots: J1, J2, J3, and J4. The first thing that really stands out is that if you're a physicist, the number you probably care the most about, the one you want to get the sequence that it's holding the most from, the fine structure constant, right? It's responsible for all the structure in chemistry, for everything to do with the electron. The fine structure constant is really, really important, and it's dimensionless, so it can't be argued away as important because you don't understand the bases. Even without the bases, it's important, so it's right in your face. It turns out that the fine structure constant is equal to this first solution squared. So right down here in this structure has 4 pieces making a sphere. The first piece is the fine structure constant. So it has 3 siblings. There's 4 fine structure constants. 2 of them are both one-dimensional each, and 2 of them are two-dimensional, by which I mean this. The solutions to this balanced equation, a little bigger, there we go. Here's the equation, here's the solutions, 1, 2, 3, 4. The first 2 are one-dimensional numbers. The outputs are one-dimensional numbers. The second 2 are both two-dimensional numbers. They have a real and imaginary or complex. They have 2 different parts. So it's a number that's made of 2 things. You can't put those 2 things together because they're in different dimensions, is the point, okay? So they come with 2 parts. Real, or the radius and theta are different expressions of this construction. In fact, let me go to the picture down here. Here's our picture in the plane of where they're actually labeled. Here's J1, J2, J3, J4. These are both one-dimensional. These are two-dimensional because they have an X and a Y component each. Okay. These numbers turn out to be, well, this is the claim I'm going to make. The Planck constants and these hyperbolic partition constants of the Planck structure are incredibly useful for understanding the algebraic geometric scripts built into the world. The ones that we see as powerful mysteries, like, wow, why is that there? We're going to start to see some of the structure that makes that there. Let's follow some of the powerful features that these constants actually have. When we take the product of all 4 of our solutions, J1 times J2 times J3 times J4, we get a circle. If we take the sum, we get 0. If we take negative sum, we get 0. If we take their quadrants, which are both of these, we get spheres. Now, already we have a fantastic algebraic geometric set. A fantastic set. We have something that quadrants as a sphere, produces a circle, and maintains a balance. Okay, that's a fantastic start for descriptors that are giving us information about the world and its division structure. Well, let's go further. These constants also have certain symmetries. You can break up just the real and imaginary part, right? We can talk about just the real part of this number. So the real part of J4 would be just this part. The imaginary part would be just this number. Not with the I, just take the number and that's the imaginary part, okay? So we can talk about relationships. Je1 plus Je2 is equal to -2 times the real part of Je3, and it's equal to -2 times the real part of Je4. Let's get a little picture for y. If you add this number to this number, you're adding this x component and this y component to this x component and that y component. The y components cancel and the x components add, so you end up somewhere over here, right? So that's going to be a value that's just real, and so it can be equal to other things that are just real. Great. So there's a lot of structural symmetries, algebraic structural symmetries in the j's, in the solutions to this hyperbolic structure partitioning, the partition solution to this hyperbolic structure restriction, this equation, right? They have all of these algebraic rules. At the same time, they're always maintaining all of these rules. The richness is quite baffling to me. And let's look at these two examples. We have two ways of combining all of the j's to get to two more circles. You can take, on the lower one here, take a sum of all the byproducts. Take every je, whether they're the same dimensions or not, take every byproduct and then add them up, you get a circle. Or take the byproducts of just the one-dimensional ones and the two-dimensional ones, and then add it to the product of the sum of the one-dimensional ones and the two-dimensional ones. You get another circle. These algebraic dividers return to circles in several ways. It's a fantastic connection. If you follow what I'm saying, I'm sure you're excited. It also has a structure that goes many ways to squaring the radial structure. So the square radial structure has many prescriptions, and the fourth power, which means the quadrants prescription, has symmetrically all these ways of maintaining the same set of rules. So the power of rules, or the set of rules we just go through right here, just these symmetry sets right here, are all these, well, the main set of connective rules that I've found in the partition constants themselves, the solutions for how we break things up hyperbolically. Okay, some of them can be summed up like this: a relationship between the product, sums, and the quadrants, or between a cubed product and a square sum. Very related. Okay, now since we've done this, since we've looked into these numbers, let's take a quick glance, just for fun, at the subsets of this set right here that are related to the construction and the constants of nature. Okay, so let's switch over. Here's the set of constants of nature, our most up-to-date set of prescriptions that decode the geometric arrangements between the boundaries and the Planck constants that each constant of nature gives us. So we took each constant of nature and we back decoded all of this to find this pattern. But the pattern is absolutely gorgeous. The first thing we want to notice is that the pattern itself has, on the right-hand side, operations in terms of the j's, and they're arranged by that. So we have two sets of sums, three sets of sums. We have square sums in two sets and square sums in three sets. So those are all the sums. And we have rows that are products of 3 and products of 2. Je squared is equal to Je3 times Je4. So this is a whole row of products of 2. And products of 2, save these two are just single J's. So it would be a square root of Je3 times Je4 in that sense. This can be rewritten in terms of Je squared also, but the whole row is Je squareds. And then rotations. So the structure here in general is taking the sphere, dividing it in our hyperbolic way, under our hyperbolic rule, which has 4 different roots, and those 4 roots have partial set descriptors, or in the connections between those 4 roots, the rules and their connections, there's partial sets. And the partial sets seem to be giving us all of the constants of nature. This is absolutely gorgeous. We're talking about the constants of nature, the most valuable, most interesting puzzle there is, question there is, because when these symmetry patterns are understood, it brings us to a different kind of world, right? One where we think of a different kind of world and we understand the world differently. So anyway, I just wanted to look through some of these things real quick for the 18/32 construction that we were seeing on the other poster. 18/32, we'll call out on the other ones that show up, the things that are familiar. There's lots of 4π pieces, all the Zhou ones show up on the left. Here's another 32. Let's go, there's an 18 over here. All right, 8, 8, 32, 32, 32, 18, 18, 18, 18/32s with 2 pi's. We get a gamma of 5/4π. By the way, these two are phenomenal. Let's just zoom in this real quick. The mass of the neutron and the mass of the tau are coming from the atomic mass constant as their boundary. And what are they doing to the boundary? In both cases, they're doing the perpendicular or the orthogonal things, square root of the orthogonal base of our structure. Remember when we first made our first real piece, it was this squared, and it was this squared. So these are both square roots of our actual first division structure, defining the mass of the neutron and the tau. Fantastic. Anyway, there's lots of symmetry in here. 18s again, a bunch of them. Let's zoom over to the other side over here. We got, oh, here's a really fantastic set. Where does this start? Okay. 18/32 all the way down in this set. 18/32s in this set. Let's go down and watch both rows. This whole set are still putting in relationship 18 and 32 degrees of freedom. All the way down on the left-hand side here. We got one popped up with 18 there. 32/18 twice in this one. Okay, so we're starting to see a lot of uniformity in the story. But I hope that some of the degrees of freedom are starting to be popped. All the puppies that over 8, all 8s, right? These are all degrees of freedom that maybe you're familiar enough for you to guess. What does the 8 have to do with? Why is it the universal parabolic constant times I over 8 every time? What's the 8 divisions about? The mass boundary has exactly 8 divisions. Remember, the charge boundary has exactly 18 divisions. The temperature boundary has exactly 32. So this structure is matching extremely well with the division structure from the Planck constants, of course, and it's also using the Planck constants as its boundaries. Okay, so we're getting a lot of confirmation, a lot of symmetry in the story here. I'm hoping it's enough to keep everyone investigating. But remember what we have in mind here. Think of this as like a Laura Croft investigation of reality. We have a secret that we know has an answer. There's a secret there for sure. It's not a secret someone made up either. It's a secret about reality. Okay? We know for sure that there's structural information about what reality is that we don't grasp. Right? There's stuff about what quantum mechanics is doing that we don't understand. That's why it's baffling to see the effects of quantum mechanics. But when we get to the point where we understand it all, we get to move on to a whole different set of equations or a set of questions, but also a different way of engaging with the world, a way that's hopefully more engaging. Well, by definition, it's more engaging. It's seeing more of the actual world, seeing the features that we only know now as constants of nature, and we may only know because we've looked up from Wikipedia or Encodata and seen the string of digits, but we might never even measure them ourselves, so we're relying on other people's measurements, right? Being able to see the structure that makes them takes you to a whole different level, where you're not just relying on someone else's view of the world, but you're grasping a view on the world that has those features. Anyway, kind of a bit ranting, but I think it's really exciting that we have the whole set here from these small set of parameters. 5 Planck constants. We have 4 J's. There's 2 other ways to represent 3 and 4, right, with r and theta, but 4 J's for our division structure. And then we have the features of the constants in geometry that represent the most predominant and beautiful geometric constants there are. The Giesking constant, the hyperbolic figure 8 knot, the Catalan constant, the domino tiling constant, the Dimmer constant, I, pi, the universal parabolic constant, S, L, L1, L2, Cu, GGA. All of these are geometric definitions and related to hyperbolic structure. Okay, so this is where we're at right now, or this is where I want to end the video. I think this was a super exciting year. We're at a story right now where we have one division structure. It's got several degrees of freedom in it, but one division structure that's bound under this set of rules. Okay? One set of balances between its solutions. Solutions of what? Solutions of the hyperbolic division structure itself. Okay? That one set gives us a story of a world that's in projection, a projected sphere that's balanced, and it produces a circle. So it's got some throat, there's some circle happening somewhere. Okay? But it makes something that exists. It's an existing form. And in fact, this is the smallest possible quantum hyperbolic form. What's the next one? 2 pi squared. I think you can make more loops down there, right? So this is the smallest, simplest one, based only on the degrees of freedom available made by the hyperbolic figure 8 naught. Okay, so the subset of this simple structure, here's the structure. Take a subset of the structure, 3 sets, 2 sets that give us real outputs, and those real outputs will be related to real expressions in the structure. Really fantastic. So any subset of this structure that you can take that's plural, it's got to be more than one piece involved, that gives you a real output will map to these constants. Great. That's the division structure, we think, then, therefore, of the whole balance between the Planck constants. This is what we're revealing. And the longer we look into this structure, the more there's the Planck, the proton mass related to one we mentioned a few minutes ago. Also the same left-hand side as the neutron mass. Okay. When we do, we can now understand these things in a new way, which always leads to taking advantage of things in a new way and framing the world in a way that then makes it easy to take advantage and see and relevantize the actual structures. We're making relevant more degrees of freedom that are in the world. We're seeing more than we saw before. And that's the process. Whether we're seeing correctly is always the debate, right? The way we determine seeing correctly is you frame a world, you see a world that starts with a framework that has certain rules built in. Those rules lead to consequences, and if those consequences match the actual measured consequences that repeat themselves over and over in the world, every time we measure them, we find them, that's how we match to the actual world. That's how we know we're seeing correctly. So until we can see, so you can visualize what an electron looks like, what a proton looks like, we can all the features of an electron look like, what all the features of a proton look like, and why they're connectively built into a world. You're not seeing the whole world, right? So it's exciting. It's exciting to be woken up so much so to the features of the world that we're still missing, and to explore what those features, as we get these clues, and turn them into actual prescriptions for how things are fitting together. It's exciting to then see features that you'd never seen before. It's also exciting where this is going to go. So our goal, of course, is then to use this as a coding logic to build a framework, a computer, that uses these exchanges directly instead of indirectly. So we can make a computer that's built on the logic that cannot be beat. The logic will beat the logic of physics in the computer. It's not going to be a higher level mirroring in a partial set. The advantage of that is that when you go down to the bottom level, you're also not building from building blocks that are artificial. You're only building from building blocks that atoms are actually built from. The ones that are the most universal and can do all the things we've seen atoms do. It's a lot of things. It's not infinite, but it's a lot. Well, it becomes a combinatorial explosive, so it goes to infinity in combination. But on the base, it's coming from a very small set as we understand the different actions that these boundaries are putting into reality. We can really start to build a machine that uses them. So that's the goal. So anyway, that's the end of the year, basically. This is we've made a lot of progress. We've got an actual prediction for every constant of nature, 288 of them here. Every codata constant of nature, we've got an exact prediction for, right or wrong, and it gives us something to test, right, as better measurements come along. But more importantly than giving us a prediction, we were matching to the predictions. So more importantly than that, by matching symmetries to the predictions, or to the measurements, I should say, we were matching to the measurements to make our predictions. By doing so, we revealed and uncovered an incredible pattern, incredible patterns, right? I mean, we take the constants of nature and decode them in this very specific way, this two-part way that has this plus or minus sign there, but always this boundary, scaling things to the right scale for our hyperbolic space. And look, here's a constant of nature that pops out. Here's a second one. Here's a third one. Here's a fourth. And look at all the first 8 here they're all half. 4 of the halves are imaginary. 3 of those are negative and 1's positive. The first half, 4 of them are real. 3 of them are positive, 1's negative. The opposite. Look, we got 8 constants of nature that define a simple recursive, spiraling to infinity internally cage. Right? It closes against itself. It's got its 4 real halves. It's got its 4 imaginary halves. And both of those come in 3-to-1 signatures, like 4-dimensional space-time. Great. There's lots of, the whole column all the way down here. These are all different constants of nature being kicked out, all under one symmetry exchange. One set of patterns here, making this many constants of nature. It's a beautiful, beautiful look into the actual structure of reality, to see these patterns, right? So I hope everyone that's excited about this and excited about trying to lift us all up as a species into a world with more understanding and a world where we're able to, with more ease, use the features of the world around us to do the things we want. Instead of having to rely on others or structures and systems to get the stuff we want, we become more self-empowered to do it ourselves. You got to learn a lot more, but every time you do, you'll be empowered more. It's worth it. It's not going to be a waste of your time. It's going to make it so you can do something more for the rest of your life. So anyway, this is a fantastic discovery, I think. We're going to keep pushing forward with all of our goals. Anybody interested in joining us for some of our week-long conferences, feel free to get a hold of Matthew, and we will be arranging some event in February. We also have an event in April for those interested in going to the eclipse. We're going to be doing a traveling event and hitting many beautiful sites and slot canyons and stuff along the way. Also going to be joining a podcast with some friends. So if people are interested in joining this discussion and this effort and participating over here at the Physics Monastery, get a hold of Matthew and we'll talk. It's really a matter of being on the conversation. If you can devote your consciousness to trying to make sense of the story of reality, then we just got one of the best things to figure it out, right? Even still better than an AI. Your consciousness always wants to figure out its reality. So when it figures out this new level of figuring out reality, I think it catches you on fire. You just get really excited. It can't stop. Yeah, it's a superpower. And it's a superpower that keys you into, oh, there's a lot more superpowers coming.